Namaskar, dear viewers, welcome to the lecture series on food technology. Today, the topic downstream processing of fermented foods or products will be discussed under the following subunits. 1. Introduction. 2. Solids or insolubles removal. 3. Primary product isolation. 4. Purification, and at last 5th product isolation. Coming to introduction. The extraction and purification of fermented products may be difficult and costly. Ideally, one is to obtain a high quality product as quickly as possible at an efficient recovery rate using minimum investment operated at minimal cost. Unfortunately, recovery costs of microbial fermented products may vary as low as 15% to as high as 70% of the total cost. Obviously, the chosen process and therefore its relative cost will depend on the specific product. If a fermentation broth is analyzed at the time of harvesting, it will be discovered that the specific product may be present at a low concentration in an aqueous solution that contains intact microorganisms, cell fragments, soluble and insoluble medium components and other metabolic products. The product may also be intracellular, heat labile and easily broken down by contaminating microorganisms. All these factors tend to increase the difficulties of product recovery. To ensure good recovery or purification, speed of operation may be overriding factor because of the labile nature of the product. The processing equipment must be therefore be of the correct type and also the correct size to ensure that the harvested broth can be processed within a satisfactory time limit. The choice of recovery process is based on the following criteria. 1. The intracellular or extracellular location of the product. 2. The concentration of the product in the fermentation broth. 3. The physical and chemical properties of the desired product. 4. The intended use of the product, and 5th, the minimal acceptable standard of purity. 6th, the magnitude of biohazard of the product or broth. 7, the impurities in the fermenter broth, and at last 8th, the marketable price for the product. The various steps followed in the extraction of fermented products together with the approximate level of purification obtained each stage are given in the following table 1. The procedure followed within each stage depends of course on the material being extracted. The product sought could be the cells themselves, such as in yeast manufacture, or large in the cells such as in the streptomycin or some enzymes, or free in the medium as with penicillin. In this table, conventional steps followed in the purification of products will be discussed. Step process, there are 4 different steps. 1. Removal of insolubles such as filtration, centrifugation, decantation by 0.1 to 1% if product solubles recovery, 90 to 90% if product is cells such as yeast. And in second, primary foam isolation of the product, the step process, sorption, physical and or ion exchange, solvent extraction, precipitation results in 1 to 10% of purity. 3. Purification, fractional precipitation, chromatography such as adsorption, partition, ion exchange or affinity chromatography, chemical derivatization, decolorization results in 50 to 80% of purity. And 4th, final product isolation by the process crystallization, drying, solvent removal results 90 to 100% purity. Coming to second, solids or insolubles removal. In general, the initial step separates solids from the liquid fraction, thereby facilitating further extractive steps such as sorption, solvent extraction, which would wasteful or near possible if the cells were not separated. In a few cases, no separation takes place, such as in the acetone butanol fermentation, where the entire beer is used. In most cases, however, the separation methods used are filtration, centrifugation, decantation and foam fractionation. Where the required fractions is in the cells, then much of the impurities are removed with the filtrate after the cells have been isolated. The various methods used in solid removal are discussed below. 1. Filtration. The rotary vacuum filter. One of the most commonly used filters in the industry is the rotary vacuum filter, which is available in several forms. Essentially, the filter consists of a hollow rotating cylinder divided into 4 partitions and covered with a metal or cloth gauze. A vacuum is applied in the cylinder, and as it rotates, the vacuum sucks liquid materials from the shallow trough in which the rotating cylinder is immersed. For thick slurries which are difficult to filter, for example, aminoglycoside broths, a thin layer of filter aid is first allowed to be absorbed on the cylinder. Later, the filter cylinder with its thin coating of the filter aid is allowed to rotate in the trough in which the broth is now placed. Ring and wire type filters. These filters consist of a coating of diatomaceous earth and a wire mesh supported by a frame of metal rods. The liquid to be filtered is introduced under a pressure of 75 psi, that is pounds per square inch, rather than under a vacuum as in the rotary vacuum filter. They are used when the load is light, such as for polishing beer or fruit juices. They can be cleaned by backflushing with water. Second, centrifugation. Centrifugation is not widely used for the primary separation of solids from broth in fermentation beer because of the thickness of these slurries and the fact that many industries have operated successfully with filters. In the enzyme isolation industry, however, centrifugation is preferred to filtration, probably because unwanted cell debris are quite efficiently removed by this method. A large number of centrifuges are available in the market, and a new fermentation industry or a change in the production method of the old processes may require the use of centrifuge for primary separation. Coagulation and flocculation. Coagulation is the cohesion of dispersed colloids into small flocks. In flocculation, these flocks aggregate to form larger masses. The first is induced by electrolytes and the latter by polyelectrolytes, high molecular weight, water soluble compounds that can be obtained in ionic, anionic forms. Bacteria and proteins, being negatively charged colloids, are easily flocculated by electrolytes or polyelectrolytes. Sometimes clay or activated charcoal may be used. The net effect of the flocculation is that colloid removal facilitates filtration. It may even be possible to merely decant the supernatant once large enough flocks remove the solid portion of the beer. Since flocculation depends on cell wall characteristics, the agents must meet the following requirements, especially if the cells and not the liquid are the required products. The flocculants should have the following properties. They must react rapidly with the cells, they must be non-toxic, they should not alter the chemical constituents of the cell, they should have a minimum cohesive power in order to allow for effective subsequent water removal by filtration. Neither high acidity nor high alkalinity should result from their addition. They should be effective in small amounts and be low in cost. They should preferably be washable for reuse. Foam fractionation. The principle of foam fractionation is that in the liquid foam system, the chemical composition of a given substance in the bulk liquid is usually different from the chemical composition of some substances in the foam. Foam is formed by sparging the bulk liquid containing the substance to be fractionated within an inert gas. The gas is fed at the bottom of the tower and the foam created overflows at the top, carrying with it the solutes to be fractionated. Surfactants may be added in liquids that do not foam. This method has been used to collect a wide range of microorganisms, and although mainly experimental, it may be used on a large scale in industry. Whole broth treatment. As had been indicated earlier, in some fermentation such as the acetone butanol fermentation, the whole unseparated broth is stripped of its content of the required product. This process saves the capital and recurrent expense of the initial separation of the solids from the broth. Coming to the third, primary product isolation. After separation of the broth into the soluble and insoluble fractions, the next process depends on the location of the desired product, such as the cells themselves, as in yeast, may be desired product. They are dried or refrigerated and the liquid is discarded. Further, the final treatment such as drying will be discussed in our last subunit. The required product may be bound to the mycelia or to bacterial cells, as in the case of bound enzymes or antibiotics. The cells then have to be disrupted with any of the several ways available, such as heat, mechanical disruption, etc. The cell debris are now removed by centrifugation, filtration, or any of the other methods of removing solids, as we described above subunits. Where the material is extracellularly available, or if it has been obtained by leaching with or without cell disruption, then it is treated by one of the following methods, such as liquid extraction, dissociation extraction, sorption, or precipitation. Cell disruption. A lot of biological molecules are inside the cell and they must be released from it. This is achieved by cell disruption, that is lysis. Cell disruption is a sensitive process because of the cell walls resistant to the high osmotic pressure inside them. Furthermore, difficulties arise from non-controlled cell disruption, which results from an unhindered release of all intracellular products such as proteins, nucleic acids, or other cell debris, as well as the requirements for cell disruption without the desired products denaturation. There are mechanical or non-mechanical cell disruption methods. Mechanical methods. When the target material is intracellular, it means microorganisms are disrupted mainly by mechanical disruption of the cell. Equipment for cell disruption includes homogenizers, ball mills, and ultrasonic disruption. Non-mechanical methods. Cells can be caused to disrupt by permeabilization through a number of ways: chemical permeabilization, mechanical permeabilization, and enzymatic permeabilization. Liquid extraction. It is also known as solvent extraction or liquid-liquid extraction. This procedure is widely used in industry. It is used to transfer a solute from the solvent into another in which it is more soluble. It also can be used to separate soluble solids from the mixture with insoluble material by treatment with a solvent. In this method, the broth to be extracted is shaken with a hydrophobic solvent, that is, one that will not mix with water, allowed to settle, and the solvent which should contain more of the material to be extracted is removed. This may be done in a small laboratory scale in separating funnels or in a stir tank in industry. The separation may be done in a stir tank in one of several ways. One, batch wise in a single tank and the solvent with its solute drained, or a continuous with a mixing and a setting tank. More efficient extractions are achieved with continuous addition of solvents. A cross current arrangement in which successive solvent extracts will be progressively more diluted, and at last counter current fashion in which efficient extraction is achieved with less solvent usage. Ion exchange adsorption. Ion exchange adsorption is one of the several adsorption methods which include chromatography and charcoal adsorption. Ionic filtrates of fermentation broths can be purified and concentrated using ion exchange resins packed in columns. An ion exchange resin is a polymer, normally polystyrene, which electrically charged states at which one ion may replace another. Synthetic ion exchange resins are usually cast as porous beds with considerable external and pore surface where ions can attach. Whenever there is a great surface area, adsorption plays a role. If a substance is adsorbed to an ion exchange resin, no ion is liberated. Testing for ions in the effluent will distinguish between removal by adsorption and removal by ion exchange. Precipitation. The insolubility of many salts are used in the selective isolation of some industrial products. It is particularly useful in the elimination of proteinaceous impurities or in the isolation of enzymes. Salts are precipitated by one of several methods: adding inorganic salts and are reducing the solubility with the addition of organic solvents such as alcohol in the case of enzymes. Lactate and oxalate salts of erythromycin have been so isolated, and citric acid has been isolated with its calcium salt. Purification. The methods described earlier isolate mixtures of material similar in chemical and physical properties to the required product. The methods used in this section are finer and further eliminate the impurities, thus leaving the desired product purer. Chromatography. In chromatography, the components of a mixture of solutes migrate at different rates on a solid because of varying solubilities of the solutes in a particular solvent. The mixture of solutes is introduced usually as a solution at one end of the solid phase, and the solvent, that is a solution which separates the mixture, flows through this initial point of the mixture application. Fermentation products are separated any of the following chromatographic methods, where the separation of the solids occur for the reasons given in each of the following. Adsorption chromatography, for example, paper chromatography. Variations in the weak forces binding solutes to the solid phase. Partition chromatography. A more solvent is passed through a column containing an immobilized liquid phase. The solvent and immobilized liquid phase are immiscible. Separation occurs by the different distribution or partition coefficient of the solutes between the mobile and immobilized liquid phases. Ion exchange chromatography. The difference in the strength of the chemical bonding between the various solutes and the resin constitutes the basis for this method. Gel filtration. This depends on the ability of molecules of the different sizes and shapes to permeate the matrix of the gel swollen in the desired solvent. The gel can be considered as containing two types of solvent, that within the gel particle and that outside it. Large particles which cannot penetrate the gel appear in the column effluent after a volume equivalent to the solvent outside the gel as emerged from the column. Small molecules which permeate the matrix appear in the effluent after a volume equivalent to the total liquid volume with the matrix as emerged. Carbon decolorization. Some solids are able to absorb and concentrate certain substances on their surfaces when it contact with a liquid solution or gaseous mixture. These include activated charcoal, oxides of silicon, aluminum and titanium and various types of absorbent clays. Absorbents have been used for the adsorption of antibiotics from broths, removal of colored impurities from the solution of an antibiotic, sugar or even from gasoline. In the fermentation industry, activated charcoal has been most widely used because of its extensive pores which confer on it large surface. Furthermore, the pores are large enough to allow the passage of the solvent. Activated carbon, powdered or granular, is used to remove color. Thus, penicillin solution is usually treated with activated carbon before the crystallization of the amino salts. A single stage batch wide system of mixing the solution with carbon followed by filtration may be used. Multi-stage counter current decolorization is far more efficient per unit of carbon than batch. Before using adsorbent, it is important to determine experimentally the most efficient depth of the adsorption zone which will thoroughly remove all color. Crystallization. Crystallization is the final purification method for those materials which can withstand heat. The solution is concentrated by heating and evaporation at atmospheric pressure to produce a super saturated solution. Many fermentation products will not, however, withstand heat, and the initial water removal is made by heating at reduced pressure or by lowering the temperature to form crystals which can be centrifuged by leaving concentrated liquor. It yields compounds which are highly potent, more stable and free from colored impurities. To obtain crystals, first a supersaturated solution is produced. Secondly, minute nuclei or seeds are formed, and thirdly, the molecules of the solute build on the nuclei. Crystalline particles from a previous preparation may be deliberately introduced to produce the nuclei. In procaine penicillin production, fine crystals are used to induce crystallization, whereas in dihydrostreptomycin sulfate, addition of methanol brings about crystallization. Product isolation. The final isolation of the product is done in one of the following ways: processing of crystalline products, drying of products direct from solution. Crystalline processing. Crystalline products are free filtering and non-compressible and therefore may be filtered on a thick beds under high pressure. This is usually done on a centrifugal machine capable of developing very high, about 1000-fold gravitational force. The crystals are washed to remove adhering mother liquor. After washing, they are dried by spinning or further drying or solvent removal. Drying. Drying consists of liquid removal, either organic solvent or water, from wet crystals such as was described above from a solution or from solids or cells isolated from the very earliest operation. Several methods of drying exist, and the one adopted will depend on such factors as the physical nature of the finished product, its heat sensitivity, the form acceptable to the consumer, and the competitiveness of the various methods in relation to the cost of the finished product. Drying can be considered under two heads: one, liquid phase moisture removal, and the second, solid phase moisture removal. Liquid phase moisture removal. Liquid phase moisture removal involves drying by heat. When drying is done by heating, the processes may be broken down to the supply of heat to the material and the removal of the resulting water vapor. The simplest method is by direct heating, in which heated atmospheric air breath heats the material and removes the water vapor. In others, the heating is done at reduced pressure to facilitate evaluation of the water vapor. Under such conditions, indirect heating from a heated surface radiation, for example infrared, or both is used to supplement the heat introduced by reduced vapor pressure. The actual method of heating is done in a number of different mechanical contraptions such as tray dryers, drum dryers and spray drying. Solid phase moisture removal, that is freeze drying. The equipment used in freeze drying is essentially the same as the vacuum dryer described earlier. The main difference is that the material is first frozen. In this frozen state, the water evaporates straight from the material. It is useful for heat labile materials such as enzymes, bacteria and antibiotics. In conclusion, in some of the fermented factory, recovery equipment cost 4 times more than the fermenter. The necessity of having a well planned and reliable recovery process and an efficient recovery plant is therefore of utmost importance. Thank you.